All right. Good morning. How's everyone today? Thumbs up. So. Okay. All right. So let's continue the discussion of the sort of overall history of the universe and the different eras that we have. And then we'll, by the end of today's class, we're going to talk more about the notion of energy conservation. Okay. So at the end of last time, um, we summarized how the scale factor depends on time in these different eras. And so just to be clear, there were some questions about this. To be sure, there's only one scale factor. There's a global scale factor, A of t, for the whole universe. And so for these formulas I was putting down, which I'll recap right now, I'm only saying this is the approximate formula for A during that particular era. Okay. So in the matter era, W is 0. Last time we derived that A of t, well, we already knew this from Newton, it was t to the 2/3. Okay. And I'm just saying that's a very good approximation during that era. The deeper you are into that era, the more exact this formula is. Hubble, by the way, which is A dot over A, you can then just compute, and so you get 2 over 3t. In the radiation era, which is W of a third, last time we found that A of t was then t to the 1/2. Okay, so again, that's just valid during the radiation era, the earliest era of the universe. This is how the scale factor depends on time. And then Hubble, which is again A dot over A, means you just pull down a half. So you get 1 over 2t. Okay, so again, during these eras, Hubble versus time is very similar, but there is a half versus a 2/3. Okay, so this matters at some level. And then finally, we talked about vacuum energy with W of -1. And there we found that our power law result did not apply. We have to go back and resolve the equation. And the solution was an exponential in time. The A of t we found at the end of last time is just E. You could write, for example, I could write H sub vacuum, for lack of a better name. Okay, some characteristic Hubble scale where HV, I'm calling it, is just defined by the energy density of the radiation, of the vacuum energy. And that's just a constant. That's also H. That's why I called it that. A completely vacuum dominated H is just a constant. Okay, so if we plot, H versus T, and let's say, well, let's just do it on, a linear scale for now. Well, you can imagine trying to draw a curve that transitions between a 2/3 prefactor and a 1/2 prefactor. It's a little tricky to draw, but you can easily imagine. It's basically 1 over t for a long time. Okay, and there's some little bit of a transition here from the 2/3 to the 1/2. Is that all right? Which I won't attempt to draw, but you can easily imagine some interpolating function that transitions the prefactor. But more interestingly is that at late times, the theory predicts it approaches a constant. So this would have to do something like this. Because at late times, vacuum energy is the thing that's dominating. We're going from here to here to here. I sort of wrote it in the wrong order, but that's okay. Is that all right? So let's say if it's on a linear scale, if you think of this as billions of years, radiation is way at the left here that we almost can't see it on a linear scale. So maybe let's put that aside for the purpose of this plot. And here it's just 2, 3 over t to a very good approximation. And then here it's a constant. Okay. And somewhere around here is the transition where you have roughly half, say about here somewhere, is where you would have, say, half the universe is matter and half is vacuum energy. And so there's some function that interpolates between these two curves. If I just do the asymptote, the 2 over 3t asymptote, right? If, in other words, imagine a universe that had no vacuum energy, aka dark energy, right? That would just be this curve. So in red, it would just be a curve that comes down and keeps on going, asymptoting to 0. Okay, so this red would be, say, matter and no dark energy. Okay, so in a minute, I'm going to recap how we compute the actual time intervals, right? So you want to know how long it takes to get, say, the end of the radiation era, or you want to get to when today is. And the time it takes to get to today is something you computed on the last homework. Okay, so you had some nice integral, and we're going to recap because I want to say something else about those formulas in a minute. But this picture here is also useful to think about as opposed to just some fancy formula on your homework, because it gives us a visual idea as to why the dark energy helps to prolong the history of our universe. So in pure matter only, right? If we had pure matter only, we just invert this formula and we will get T today would be 2 over 3 H naught. And H naught we know, right? H naught, let's put it here. About here, let's say. This is H naught. This is like 0.7 times 10 to the minus 10 inverse years. And that's a number we know because we've measured the local expansion rate of the universe. Like we've measured it today. And so you see these two curves then, you can think of the age of the universe, the whole history of the universe. One way you could state what that means, right? I mean, physically we know what it means, just how long a clock that's been sitting there has been ticking. But another way of saying it is the age of our universe today, T naught, is the time it has taken H, which started off at some extremely high value up there, to drop all the way to H naught. Right? There's only one moment we think when it was H naught today. So it's the time elapsed to reach the current value. Does that make sense? So in other words, if I go here and I draw a little dot there, where that is the same height as this is T naught. Okay. Excuse me. But if you had only a matter-dominated era, where it's this 2 over 3t, the time at which it has dropped to H naught is back here. That's this formula. That number there, this is T naught, let's call it, I don't know, twiddle. This is the wrong theory. Okay, just the T naught according to a matter-only universe. Okay, and if you plug in this, so you just take the 0.7 and invert and put in a 2/3, right? This number is like 9.5 billion years. Okay, but you see visually that it's going to be a younger universe, this interval versus this bigger interval in a universe that has dark energy. Okay, so Hubble, because of the dark energy, has been falling, but not falling as quickly. So it took longer to reach today's value. Okay. So, yeah, so other questions about that? Right. Okay, and then indeed on the homework, you check the T naught, you can get out 13.8 billion years if omega, if if you have 70%, let's say, dark energy or vacuum energy. Okay, so on a linear scale, it looks something similar to that, I guess. All right, so then let's talk about these times in just a little more detail. Okay, so I'm going to redo something you did on the homework. So let's write H again. And so this tells us that the time interval, dt, we can just write this as integral dA over A of H. Okay, I can just manipulate the equation to write it like that. And at first sight, this may look like some kind of circular reasoning. We're just, H is defined as A dot over A, but I just rewrote it like that, right? But this is useful because we can think of H as a function itself of A and imagine carrying out this integral. And we can go over any range we want. So often we'll integrate back to the Big Bang, though we don't have to, right? We could go just from T1 to T2 and from some A1 to A2. But often we'll set the lower endpoint to 0 because we're often interested in, say, the time since the Big Bang. And then we say that H, thinking of it as a function of A, by the Friedmann equation, just 8 pi g over 3 energy density of A. And we know how our energy densities depend on the scale factor, as we've discussed in the last couple of lectures. So for radiation, we have A to the 4. I'll set today's value A naught to 1. This discussion. Rho matter today over A cubed, and then the vacuum energy, which is a constant. Okay, so that's the sense in which H is a function of the scale factor. And therefore, you can just plug this into this formula and carry out an integral. Let's maybe have a little table to remind ourselves. So those rows are values that we need. That we can infer everything from today's values. This is the value of that species energy density, 0 for today. And we've already talked about how radiation in electron volts is 3.2 times 10 to the minus 15 eV to the 4. In matter, it's somewhat bigger. So we already wrote down these two values in the last class. But the vacuum energy, well, let's use the fact that we know that we have about, today, it's mainly these two. This one is kind of negligible, as you can see. And so this is like 70%. This is like 30%. So if you want to fill in the vacuum energy, you just multiply this number by 7 over 3, basically. Okay, so that's like 2.5 times 10 to the minus 11. And another useful thing to remember is these omegas. So if we define, say, omega for the ith species as the energy density in the ith species over the critical density, this is the capital omega, for a flat universe, rho critical is just the total density. So since we're assuming flatness, this is also just rho I over the total density. So it's literally just the percentage, the fraction of that species. And we can report at today's value. Okay, again, these are going to depend on time, just like the densities depend on time. The fractions will depend on time. So the fraction is, well, straightforward. You just ask what's this as a fraction of the sum of the three, and so on. So that's about 8.6 times 10 to the minus 5. Okay, so there's not much radiation today. 1 part 10 to the 4. And then we've said matter is about 0.3, and vacuum energy is, or dark energy is about 0.7. Okay. Now, strictly speaking, these three numbers, if you have a flat universe, should add up to exactly 1. Right? And if you sum the three of them, right, omega, sum of all the omegas is the sum of all the rows divided by rho. That's the total row divided by the total row, which is 1. So these numbers should add up to 1. Okay. As I've written it, you can see there's a slight little error at the part of 10 to the minus 4. Okay, but we can live with that, right? I mean, you can easily subtract that number, pick your poison. We don't know these numbers to such fantastic precision, okay? So if you want to subtract that number from that or from that, so they literally add up to 1, you're free to do that. But the point is we don't know them to great precision, so we don't normally write it like that. Is that okay? It's going to look a bit funny to say matter is 0.3 minus 8.6 minus 10 to the minus 5. That would just be me guessing a level of precision that I don't know. Okay, but we have good evidence that the universe is flat, so we do think they add up to 1 to good precision. All right, so let's just take this and plug it in here like you did on the homework. Okay, I'm just including all 3 species. On the homework, you just did matter and vacuum. And so then you can write this, yeah, so it's a very simple thing to do to manipulate this equation by just dividing by the total and then multiplying by the total. You can't stop me from doing that. Okay, and in this way, these prefactors are just the omegas. This is omega for radiation, omega for matter, omega for vacuum, evaluated today. And this prefactor at the front is Hubble today. So this is H naught square root omega radiation today over a to the 4. Oh, I don't mean rho, I mean omega. And then omega vacuum today. So this, most of you already know from the homework. And then we just plug it into this expression and we can compute whatever time interval we like. If we already have some knowledge of the scale factor at which you're interested in some time in the universe. Okay, so let's consider, let's go back to this plot. Plotted rho versus the scale factor. Remember that is radiation is this 1 over a to the 4. Right, R for radiation. Matter, 1 over a cubed. And then the vacuum energy is some constant. Okay, and then this moment here is A, normally called A equality. And we already checked last time that A equality is just 1 over 3600. And it's easily just the ratio of these two quantities, actually. Because you just go back a to the 4 versus a cubed. So it's literally just the ratio of those two numbers is 1 over 3600. Okay? This moment here which, as I said, doesn't particularly have a good name, but the moment at which matter and vacuum energy are equal, well, let's give that a name. I'll call it A equality, comma, MV for matter vacuum. The era at which these two species are 50-50. Radiation is negligible at this point, so we can ignore that. This one, well, who can tell me? What should A equality MV be? What will be a formula for that? What's the scale factor at which this happens at? You have to do a very short calculation, but the info is here. What kind of formula would you write for that? Yeah. You want to make them equal? Yep. That's right. Yeah. Does everyone agree with that? So basically, you've got to remember that this curve here, right, this is dropping, slope -3. There's a constant. Radiation, remember, is -4. So how far do you have to go back such that these balance, right? You just have to go back a little bit in A. So the formula would be, what you said, A equality MV is just 0.3 over 0.7 to the 1/3. Does that make sense? You just if today's value is 1, so here we are, we'll let A naught, which is 1. This is 0.3. This is 0.7 as a fraction. So how far do you go back such that these curves meet? It's just this formula. Does that make sense? Any questions about that? I don't want to seem cryptic. Yeah, and so this number, this is like I don't know, what is that number? 0.75. Is that all right? So the universe was only a little bit smaller than it is today, 75% of its current linear size. The matter and vacuum energy, these two numbers went to 0.5, 0.5 instead of 0.3, 0.7. Because you go back and the matter its density is rising rapidly relative to the vacuum energy. So you don't have to go back too far into the past for them to balance. So you imagine if you go into the past when the universe is, even a factor of 2 smaller than it is today, already matter is significantly bigger than the vacuum energy, so on. And you quickly enter a very matter-dominated era where this is, it's very quickly up to like 99% and so on. Remember, it's a log-log plot, so that's what that would mean. Okay, so with these numbers in mind, right, we could just take that integral there and carry it out. Okay, so we can make a little table. So let's look at, say we'll do this matter vacuum equality. And I put the scale factor here. So we just said that that's about 0.75. So we might wonder what's the time at which that occurs? How long did the universe take to reach this point? That's what I mean by this. Well, you would just go here. All you have to do is to say the time at which that occurs, the time of equality matter vacuum, is from the beginning to a quality matter vacuum, where this is 0.75. You have everything in the integral, just like you did on the homework for today's value. You know the omegas, we can include all 3. This term will be very negligible in that integral because it's dominated by the late endpoint of the integral, but you can include it just for completeness. It doesn't matter much. Just plug in that into there. You know the 3 omegas, they're on our table here. You know H naught. And then you just integrate, instead of up to 1, which would be today's time, which is what you did on the homework, you just integrate to 0.75. And then that will give you that moment instead of today's value. Okay? And when you do that, you get, oh, why did I wrote it? I wrote it very far away. That's okay. You end up with very close to 10 billion years. Okay? So when the universe was 75% of its current size and matter and vacuum were equal abundance, 50-50, that's happened when the universe was about 10 billion years old, according to this model where we modeled dark energy as just pure vacuum energy. Okay, today's value, as you checked on the homework, has a scale factor of 1. So you just go all the way to 1 as you did today. That's T naught. And then it becomes a little bigger, 13.8 billion years. Okay. And then we can also add to this thing radiation matter equality, which is this moment in time. Okay. That's when that was in the distant past. The scale factor was only 1/3600, a much smaller universe. And then again, you can go to this integral. And if you want that, which is normally just called C equality, you just integrate to 1/3600 to get that time. Is that all right? For that integral, you can, again, certainly include every piece. It doesn't matter. But you're so far into the past, the vacuum energy now would be completely negligible. You're just integrating from here to here. The vacuum is down by many orders of magnitude. So a good approximation, you could just include these 2 terms and ignore that, but you can include all 3 if you want numerically. So anyway, you just integrate from 0 to 1/3600. And if you do that, you'll get about 50,000 years. I may have said 70 earlier in the course. I don't know why I remembered 70, but it's about 50. Is that all clear? So this is the time. Okay, so we have this table of relevant, important scale factors and time scales. Are there any questions about this? Yep, that's right. I mean, at some level, it's all connected, I guess. But yeah, it's controlled by, if we plot Hubble versus time, there's a little bit of a change because Hubble is acting differently than you would have said otherwise. But it's a indirect connection to star formation rate. Yeah. Ah. Oh, okay. In the infinite future, yeah, it would just keep on slowing and slowing and slowing, but it would asymptote. It'd always be positive, but asymptote towards 0. That's right. And it's not on the board here, but it expands at an exponential rate. Exponentially quickly, in fact. Yeah. If the dark energy is not vacuum energy, and we'll talk more in a coming lecture to iron out what's going on with dark energy, is it really vacuum energy or not, and so forth. But yeah, if it's dark energy and it's somewhat different to vacuum energy, then there are other possibilities. But the current model that fits the data is just a constant. All right. Let's also, on that point, let's also maybe plot these omegas versus time. It's good to have a image of that. So it's really just a replotting of this thing here. But it's nice to maybe hammer home the point. So I'm going to plot omega for different species versus, it could be time or scale factor. It doesn't matter too much qualitatively. So the sum should be 1 for a flat universe. Because that's the total. It's a very boring curve. And now for the individual species, if I start with radiation, it's just this fraction, right? It's just that relative to the total. So early times, it's all radiation, so it's 1. Okay. Like this, very close to 1. And then at some point it drops, and then it just keeps on dropping and asymptoting towards 0. And this point here, which is 0.5, just to be clear, that is T equality. So that's what radiation does. Okay. So in this first 50,000 years, this is mainly dominated by photons and neutrinos. Go back further enough, you worry about electrons and positrons and so on, as we can discuss in coming lectures. But for most of the era, once the positrons have mainly annihilated away, it's mainly the photons and the neutrinos. And then the matter is starting off negligible, but then by definition, it's 50-50 at this point, and then it's dominating. Okay, that's this era, it's where it's dominant. So it's almost 1, and then it too drops. And this is a prediction for the future we're discussing. This again is 0.5. This is T equality matter vacuum. 10 billion years as opposed to 50,000 years. Let me label these. R for radiation, matter. And then the vacuum I drew in blue, but since I'm looking at a fraction now, a fraction of the universe, this is not a constant. The fraction is changing in time, the percentage. So it's 2, very negligible for a long, long time, we think. At least vacuum energy makes that prediction. And then it kicks in here and would dominate into the future. T naught is about here today. And if I've drawn it right, it should be that this is about 0.3 and this is 0.7. Okay, so that's how the fractions of our universe evolved in this funny way, where matter, especially matter, underwent a little bit of a wild ride up and down. Okay, so again, photons, neutrinos dominant, regular atoms plus dark matter is dominant, and now it seems the vacuum energy or dark energy is beginning to dominate. And into the distant future, it'll be just 99%, 99.9%, as far as you want to go, into vacuum energy domination. Now, this moment in time, right, it's 70% dark energy, and most of the matter, as we'll discuss, is dark matter. So like 25 out of the 30% is dark matter. So famously, people like to say that today we only really know about 5% of the stuff, and the other 95% is the dark energy and dark matter. Okay, and people write books on the 5% and so on, and the 95% we're ignorant of. But again, and that's true in a way, but if you look at this plot, remember that's a very time-dependent statement. Okay, so in the first 50,000 years, we have an extremely good characterization of the contents of the universe. They're our friends, the photons and neutrinos that we understand very well. And there's no indication that in that early era, there's much of anything else. Okay, so we can talk about that later in the course, why this is not just some curve that we predicted from this, but we have good evidence that this curve is right. Okay, so for example, it affects Big Bang nucleosynthesis. The success of Big Bang nucleosynthesis, as we'll hopefully have time to discuss, indicates that yes, back then, it was just good old standard model particles that we know about. It wasn't some dark stuff that was filling the universe. We have good evidence that that's not what was going on. So in the past, we had so imagine if there were observers living here, it'd be very terrible conditions to live, but imagine there were some weird species that could live in the early universe. They would not be writing textbooks, books on the 5% on Amazon. They would be talking about, my God, we understand everything. Isn't this great? Of course, they wouldn't know that there was a lot of other stuff to come that is lurking there, but just subdominant. And then conversely, in observers who are around in the distant future, they would say, oh my gosh, we don't know about 99.999% of the universe. So they would be in the other extreme of concern. Yeah. More stuff to come. So again, my statements here rest upon the so-called dark energy being literally vacuum energy. And so then it's this curve. And it's actually hard to imagine material that has a property where so for other stuff, you mean not these three things? That can happen if then for the rho versus time or scale factor has to be increasing function. It'll have to overtake the vacuum energy to be relevant. And so the short answer would be, well, we cannot know, but there are good reasons why we think in conventional particle physics, let's say, you cannot have a curve that's actually steeper, that actually has a positive gradient. The vacuum is kind of at the limit of what's allowed by standard quantum field theory. But it's conceivable that there's a surprise lurking. But there, most of us think that, yeah, you can't have a curve that's steeper than that. So maybe there'll be time to discuss some of those theoretical points later. But yeah, from the point of view of consistency of known sort of quantum field theory and so on, we think those are the three basic structures allowed. And what you could have, and when we talk more about dark energy, you could imagine it's not vacuum energy, it's something else. But the other thing that it could be that's most preferred by theoretical reasons would be a curve that has a slope, but a slope is slightly negative as opposed to slightly positive. So it will just become more and more irrelevant at later times, but perhaps always more relevant than the red or the black. So in other words, still dominating, but just not as much as vacuum energy. That's a logical possibility too. I don't expect any of that to be obvious, but we'll discuss dark energy later. Other questions? Okay. Okay, now I want to, for the remainder of today's class, well, first of all, yeah, has everyone got a clear picture of this? I mean, some people who have a background in cosmology might be like, oh yeah, I know all that. But if you don't have a background in cosmology, you want to just make sure you can really, this stuff sinks in. I don't want anyone to be left behind. Is it all right? Okay. So in the remainder of today's class, and I guess we teach again tomorrow morning, I want to talk about what's going on with energy, the total energy of our system, of the universe. So you could think of this as a little bit more of a sort of theoretical topic in a way, because these equations, we solve the equations, these are the solutions. We don't necessarily have to worry about whether something weird is going on with energy conservation. We could just say, I don't want to think about that because it's maybe too subtle. But I think it is an interesting topic, and it's a notorious question that people always ask. Okay, so let's begin by thinking about, say, a piece of our universe. Take just a random big sphere in our universe and ask what's happening to its energy. Okay. I just pick a sphere randomly and it has some radius. And I want to think in terms of physical distances. Okay, so sometimes when we talk about R, we mean the co-moving distance, which is fixed over time. And then there's the physical distance where you have to include the scale factor. So I mainly want to talk about the physical distance at this point. Okay, the literal, nothing fancy, the literal size of this thing at some moment in time. And there's a bunch of stuff in here, right? This houses some portion of the whole universe. So there's all the stuff in here, the atoms and the radiation, so on and so forth, the vacuum energy. But the size of this region, we're going to allow it to grow as that region grows. So now we can think about what is the energy enclosed in this sphere. Okay, so that must be the energy density of that sphere, the total energy density rho, times the volume of that sphere, and to be sure, the physical volume, nothing fancy. Okay, so I'm going to write this as rho. The volume is 4/3 pi r cubed. And now I want to think about the time dependence. So we know how rho changes in time or with scale factor. It's just this curve. It's the sum, like the total is the dotted thing. That's the total. And I now need to know about R physical. So how does R physical depend on the scale factor? What would you say? The physical radius of a region, how does it depend on the scale factor? Radius times the scale factor, yeah. So it's just proportional to the scale factor, nothing fancy. Okay? So if I take some region in the universe and it's full of these things, radiation, matter, vacuum energy, but then I want to know how does the total energy of that region depend on time or depend on scale factor? I just take rho and then I multiply it by some factor of a cubed, and there's some 4 pi's and whatnot. Okay, so the enclosed energy is therefore proportional to rho times a cubed. That's all I want to say. Okay, so let's now plot this. So this is the enclosed energy of some random sphere of interest. The size that you pick will affect the prefactor, which I'm being a bit glib about here, but I just want to talk about how it depends on the scale factor. Okay, so in the radiation era, rho is 1/a⁴, right? And then I multiply by a cubed. So in the radiation era, this is 1/a. Okay, so that's like this. This is radiation. In the matter era, rho is 1/a³ times a cubed, so it's just a constant. Okay, so matter looks like this now. And then finally, the vacuum energy, we have a constant rho times a cubed. So we have a cubed. So it's something like this. Okay, and then the total is just the sum . That's the total. Is that all right? Questions about that? This rho, the rhos that we've all been talking about are the T00 of the energy momentum tensor. So this is the honest to goodness energy density with a caveat that I'm getting towards. Okay, but modulo this thing that I'm about to discuss, which is the whole point. Like let's say in regular QFT, this thing is the energy density. Nothing fancy about it. This is the honest to goodness energy density. It's the thing whose integral is the conserved energy, the standard energy. The Noether energy associated time translation symmetry would be this thing. But there's a big problem because that thing depends on time. Right? You can write A here or you could write time. It's qualitatively similar. You do some stretching to go from A to T, right? It's not something, they're monotonically related. So the energy enclosed in this region depends on time. Okay, not in this era, roughly constant, but in that era and that era. So overall, there's a time dependence. Now, this is just some chunk of the universe. Okay, and we have all this other stuff out here. When we talk about energy conservation, right, we shouldn't claim that the energy of a subsystem is conserved and the energy of the Earth is not conserved because it gets all this energy from the sun. It's only the total energy, Earth, sun, etc., system that's conserved. And so, maybe you could say, well, that's just a subsystem and its energy depends on time. But that doesn't seem like that could help us at all. That won't help us at all to say that because every patch will just have that same curve, right? Who cares what sphere I pick? I could pick this sphere over here and run the same argument and it's going to go like this. Maybe the overall scaling is different because the overall height will depend on the size of the region, depend on the prefactor. But every patch in the universe is going to have its energy undergo this shape, according to this theory. Okay, so however you cut it, it seems like the energy depends on time. All right? Now, if I ask, but on that point, we could even go further and say, yeah, but still, it's the total energy is the only thing that we should check is conserved. And if the universe is flat, there are actually infinitely many of these things, right? The universe is flat, the spatial geometry is just R3. There's infinite space. Each little patch has an energy that goes like this. So if you count all the patches, there are infinitely many of them, infinitely many spheres or cubes you could put together. And so the total energy is actually this curve multiply infinity. Does that make sense? Total thing should be infinite. And so if you have a quantity that's infinite, you might say, well, I don't know, my brain breaks and I don't know if I should worry if it's conserved or not, because at every moment in time, it's just infinity somehow. So maybe somehow that's a way out of jail to make that argument. Sorry. But this, I think you would agree, is not a very good argument to just say, well, it's infinite, so who cares? But we could even be very precise and make things finite. Okay? So I'm not saying the universe has the geometry of a three-sphere, but potentially it could, right? We know that we've discussed that it could have a geometry like a three-sphere. And if it does, its radius has to be rather big, at least something like 450 billion light years, as we showed a couple of lectures ago. Because the curvature looks to be compatible with zero, but we don't know if it's exactly zero. So let's say for argument's sake that our universe is topologically a three-sphere. Okay? Now, a three-sphere has a finite volume. Maybe its radius is 450 billion light years, or maybe it's a Google light years, who cares? It's some finite radius. And so now there is a total energy that's finite. There's only a finite number of these patches. Right? Each of these patch is some ball, and you fill it up on the sphere, and you'll find there's only a finite number of balls that you can put on the sphere. Literally a finite three-sphere. And so the total energy would be finite. Perhaps very big, but finite. Is that okay? So there's definitely a finite energy, and its curve will be that. Okay, so yeah, so let's just say that. So if we have three-sphere, the total of the whole universe is the same shape curve, is finite, and a function of time. Okay, so now we should be bothered because remember the energy must be conserved by the Noether theorem. And so we should check, have we satisfied the assumptions of the Noether theorem, right? So let's see, what are the assumptions of the Noether theorem? You can tell me that. Assumptions of the Noether theorem, yeah. Need time translation symmetry, yep. The time translation symmetry is the statement that the laws obey time translation symmetry. So for example, it should be that G Newton doesn't depend on time. The electron mass doesn't depend on time. The strength of the electromagnetic force doesn't depend on time. But the laws of time translation symmetry. Well, we're just building everything from general relativity, which has time translation symmetry. So we're okay on that point. And then there's another assumption, slightly more technical. Anyone know what it is? Well, let's just state the other assumption, which we often just take for granted, is that you need a system under the umbrella of a Lagrangian or Hamiltonian formalism, or indeed quantum mechanics. So if you're under that umbrella, then you can run, as Noether did, run a derivation of the theorem. But we have that too, because even though I didn't emphasize it, the Einstein equations from which all this derives can come from an action or a Lagrangian. There is an underlying Lagrangian, the so-called Einstein-Hilbert action. We haven't written it down, but I assure you it exists and is well known. And so we are under the umbrella of a Lagrangian or a Hamiltonian formalism as well. So that combined with time translations means you must have a conserved energy. And then the conserved energy, remember, is not ever really a statement about subsystems. We're always in this business of looking at subsystems and saying, well, the energy is kind of conserved. Like if I have an atom, I say, well, as long as I isolate the atom, its energy can be conserved. So if I don't shine light on it and the electron jumps up and so on. So I need an isolated system. And so you always have to ignore the other stuff and hope that that's a good approximation. And then the subsystem will have a conserved energy. But what's better than the whole damn universe? You know, I really have taken into account everything, right? So it damn well had better have a conserved energy because I haven't missed any stuff that it could exchange energy with. Okay, so now we're going to discuss this. So I hope everyone agrees that we have a bit of a problem. Is that fair to say? Any questions about it at this point? Yeah, so where did the energy go? Where is the energy coming from? All right, so we have time, let's say the remaining few minutes, to maybe give us a clue about what's going on. And then next time we'll finish with the full analysis. So a little bit of a clue to get us thinking is, okay, so punchline is going to be that there's a piece of the energy we're missing. So when we talk about the energy momentum tensor in the standard way we introduce general relativity, we're always talking about the energy stored in matter. And I don't just mean this matter, M. I mean all of it, let's call it matter, stuff. Whether it's photons and neutrinos or whatever else, let's call that matter, just regular stuff, okay? That's the TMU that we've introduced. That's the TMU that is the thing that you put on the right-hand side of the equations. But there's something else in the universe that carries energy. You know, what's that? What else carries energy? Yeah. The curvature itself, that's a related concept. But what's a very, even just simpler idea is related, you mean the curvature of space-time? That's that's one way of putting it, and there's a related, even simpler way of stating it. Is there space-time itself, or just the energy of gravity? So gravity stores energy, right? There's potential energy in my marker. Okay? So even Newton would say that there's extra energy that we've not included when we talk about the total energy here. So we're going to have to, next time, I guess, talk properly about the energy stored in gravity and general relativity. But maybe we can use Newton for the next few minutes to give us a clue. Okay, so even the Newtonian theory can tell us something a little bit interesting, but it will ultimately come up short to explain what's going on. Okay, that is to say, we'll be able to see that the Newtonian analysis won't be sufficient. It'll be inaccurate. Okay, so let's talk about gravitational energy. So let's go back to our sphere here, radius r. Even Newton would say that there's a gravitational energy associated with this thing. Okay, if you have two separate objects, you know that there's an energy, I'll call it, I don't know, V gravity, which would be minus G m1, m2 over the distance between them r. You have 2 point masses. So, but here, let's say you focus just on this sphere here. Let's ignore everything else for the time being. Just this single sphere. So if you want to know what the energy stored in that thing is, you can't just write that, because like there's a little bit here that has some mass, and there's a little bit here and that has mass. So you have all these pairs. Every little point, you can draw a little piece of mass, and you sum over all pairs inside the sphere, right? Or really do an integral. Okay, and so you do that thing, and it's a similar thing you may have seen in, if you haven't done this example, it's not bad because it's a uniform sphere, so the integral is not terrible. You could do a similar thing if this was a uniform charge density, a sphere of uniform charge. You may have done that exercise in your electromagnetic course. And in any case, what you get is the total mass here squared, and then the total radius, or the radius. Okay, this is just what you would expect on order of magnitude grounds, right? So it's just the mass squared over the size r. The typical separation between them, well, sometimes they're very close and sometimes they're separated by 2r. So the mean, if you like, is something like r. So that sets the kind of characteristic separation. And then you do a pairwise sum of all little pairs. And so since it's a double sum, that's going to give you an m squared. And then if you bother to do the calculation, you end up with some funny prefactor of 3/5. And that 3/5 is not going to be very important for our discussion today, but it happens to be there. Is that all right? That's the energy, the self-energy stored in a uniform sphere. Okay, and to be sure it's negative, as gravity is an attractive force. Okay, so this minus sign is extremely important. Okay. Yeah, so this is just a Newtonian approximation for now. Okay, so gravity is attractive, so there's this negative energy stored in this region. So whatever the true answer is, we should take this curve here and we should subtract something. We should subtract that somehow. At least that's what we would do according to Newton. All right, so let's go a little further. So this is the enclosed mass for our region. The enclosed mass is 4/3 pi r cubed times the density of the region. And Newton would say this is just a mass density. But again, in the spirit of just giving us a first warm-up exercise into this topic, let's promote that to the energy density in units where c is 1. That's what you would guess. You'd replace m by e over c squared, right? We're going to do the proper GR calculation next time. But does you agree it will be something like this? Okay, so I just plug that into here. And then I get that the gravitational energy, I don't know, there's some 16/15, which are not going to matter for us. G rho squared. And then the physical radius to the power of 5. Okay, because there's an m squared. So here I get an r to the 6. And then I divide by 1r. So I get r to the 5. Okay, so I have that formula there. And if I come back here, the enclosed The regular energy, let's call it, I don't know, the energy of matter, so to speak, but including everything, radiation, vacuum energy, or you could call it E sub non-gravity, everything else, right? I don't know what's the best name to give it, but I hope you understand what I mean. This stuff is this formula, a very simple formula, and then Newton says you also have that contribution from the gravitational energy. Yeah. So you see these formulas are quite different. And if we plot the two of them versus r, so I pick some sphere here of radius r, just a chunk of the universe. Okay? So I could pick a chunk as small as I want or as big as I want. And we'll get these corresponding contributions. So let's plot these formulas versus r. This is an artificial r that I just choose, a sub-patch of the universe. So how do these energies compare as I consider bigger and bigger sub-patches of the universe? This is the energy in this patch versus r. So if I first just plot the sort of the regular energy of matter, or you can think of this as kind of the mc squared energy of stuff. It's just growing cubically. Nothing fancy. I just take bigger regions, so they should have more energy. The matter, so to speak. And now I want to plot the energy, the gravitational energy according to Newton, to the extent that we can trust the Newton formula. And so it's negative. We see it's r to the 5. Okay, so I start off and it's some curve that's very, very shallow. And it goes on. Maybe let's plot this is Vg. Let's also plot its absolute value so I can compare to the other curve. So let's also plot, yeah, absolute value of Vg. So just the mirror image is just this, nothing fancy. It's going like that. So at very small r, right, the gravitational energy is subdominant to the regular energy. So down here, basically, I'm taking a relatively small chunk of the universe, small r, and we're getting something that should be totally unsurprising. So, colloquially, we say that the mc squared energy of stuff is gigantic. That's the statement you're up here. And some little, negative energy from Newtonian gravity is kind of irrelevant. That's why this blue curve is way below the black curve. Right? So if I take the Earth, for example, we would normally say, the mc squared energy of the Earth is some gigantic number, and the minus whatever 3/5 gm squared over r Newton energy of the Earth is totally negligible. Okay? It may be relevant in describing how the pen falls and so on, but in terms of the total energy, it's some whopping big positive number because of the mc squared energy of the Earth. Right? So if we were to liberate the whole Earth into pure radiation, it would be some giant positive amount of energy. Right? That's the usual stuff. mc squared is huge. Okay, but now what we do is we keep on going and we consider a chunk of the universe bigger and bigger and bigger. And so now you see the r to the 5 is going to do something interesting. It's going to rise quicker and cross and go up. And there's a point at which they match. Okay, so down here, it's really negative, remember? It's going like this. Okay, that's just the absolute value. So there's some special physical, I'll call it, maybe put a star on it, where they balance each other. They're equal and opposite. Is that all right? Remember, this is negative. Just and beyond that, somehow it predicts that the total energy is actually negative. If you consider a region sufficiently gigantic, there's a huge amount of negative gravitational energy stored in that thing that's somehow beating its positive mc squared energy. That's what this formula would have you believe? Is that clear? When you're way out there. I mean, this is according to Newton. We shouldn't necessarily trust Newton. Okay. So we can check the R star at which the crossover occurs. So let me rewrite that formula on the right for convenience. Right, this is minus. Okay. I just broke this up. Okay, so like there's an R to the 5, I broke it up into an R cubed and an R squared. There's a rho squared, I broke it up into rho, and so on. Okay, just a separation. But the reason I did that is because this prefactor here is actually the energy of matter. Okay, and I want to compare the two. So it's good to pull out that prefactor. So this is E matter, all the non-gravitational stuff. And this thing here, putting aside the 4/5, remember that Hubble squared by the Friedmann equation is 8 pi g over 3 rho. Right? So this bit here, which happens to be 4/5 pi g over rho, is almost h squared. Is that all right? It's just that the 4/5 instead of an 8/3, but that's just a prefactor. Okay, so this thing is actually minus the energy of matter. This is almost Hubble squared. And then there's some R squared left over. Okay, and then because the 4/5 instead of an 8/3, there's some silly prefactor that we don't care about too much, which happens to be 3/10. Okay, that's just a rewriting. Okay, so then you can just say, what's the point at which they match? Right, that just means that the 3/10 times h squared R squared equals 1. Then this will be EM. All right. So, well, I'll put it over here, maybe. So 3/10 h squared R physical squared star equals 1. That's when they're equal. They're both equal EM. And so then you learn what R physical is. So if I did it right, it's root 10/3. And then it's 1 over h. Our formula. Okay. Remember I set C equal to 1. Where do I put the C? Do I need a C to fix this thing? Where should I put the C, if at all? Yeah. In the numerator, yeah. It's a length, 1 over h. H is inverse time, so looks like R length equals time. So I fix that with a C. Okay. Now this thing here, okay, so that's that. That's the number. As I'm about to explain, Newton is not very accurate in this regime, but put aside some root 10/3, which is like 1.8 or something. It's a kind of order 1 prefactor. This is on the order of C over h. That's what we should remember from this. This is on the order of C over h. Here's our friend, the Hubble length. Okay, that I often wrote as dh. Okay, so somehow when you're out at the Hubble length, Newton predicts that the gravitational energies, let's imagine this is the Hubble length now. Okay, there's some root 10/3, so let's not worry about that. When you're at order the Hubble length, somehow the negative gravitational energy stored in this thing is as big and negative as the mc squared energy of the whole thing, when you consider a gigantic patch like that. Okay? So something on the order of the Hubble length, which is order the observable universe. Okay? If we go to a region bigger than that, right? So if now this region is so big that, say, this is dH, now that's the Hubble length, and you consider a patch even bigger than that, Newton's saying, well, you're out here somewhere, and the whole energy is actually negative. Okay. Now, this is the point at which we wonder, should we trust Newton? Okay? Because you see this length scale here, which this interesting stuff is going on, has a C in it. Well, that's alarm bells going off that you shouldn't trust Newton at that scale. You've gone so far that the scale itself knows about C. Okay? And it's not shocking that we had to go out to a scale that's so big that it has a C in it, because that's the scale at which you're balancing a Newtonian formula, has no C in it, to mc squared. So there has to be some parameter that knows about C. So you pick R to be so big that it's order C. This is right on the edge of where you can trust Newton. This is precisely where Newton starts to give you order 1 errors. Okay? If you're within, say, a factor of 10 smaller than that, so you're back here somewhere, even the Newtonian formulas are pretty good. Okay, it's a bit of a long story, but this is kind of analogous to imagine doing kinematics, Newtonian kinematics versus Einsteinian kinematics, when you're studying particles that have a speed of, say, a half c. Okay, if particles have a speed of like a half c, Newton is not terrible, but it's not too accurate, right? You're going to have like factors of 2 and so on errors. When you're at distances of order c over h, that's when the Newtonian, say, formula over here is going to start giving us factors of 2 errors and so on. So we shouldn't worry about the formula in its entirety. So roughly, out here somewhere, and I cannot be too precise, let's just draw a wiggly line. This is where you cannot trust Newton. Okay, and back here is where Newton is accurate. But precisely where the Newtonian formula is starting to fail, it's an interesting thing that I hope conceptually you'll see, that the gravitational energy is somehow trying to cancel the mc squared energy. At least the Newtonian formula says that. Is that fair to say? But we care about the whole universe, maybe on a 3-sphere or some big thing, which is much bigger than this. And now we just entered the regime where we cannot persist with this formula. This formula is junk out here, I can assure you that. So don't pay too much attention to that blue curve blowing up. It is way off. Okay, it's like trusting Newton now. If you're out here, it's like trusting Newton when the speed of a particle is 0.99999 c. It's not good, not a good idea. Okay, so we have to deal with this properly using general relativity. And it turns out the formulas for energy and general relativity are actually extremely elegant. They're a little bit subtle, but we're actually not going to have to do formulas that quite look like that anymore. There's going to be some very nice formulas, and they're going to resolve this thing completely. Is there any questions about this? Okay, so we'll pick this up again tomorrow morning. Thank you.